My name is Emanuele Di Lorenzo, and today I will talk about the predictability dynamics of the inner shelf flows around Point Sal. This is work in collaboration with other co-PIs, Kevin Haas, Art Miller, Christopher Edwards, Angie Moore, Nirni Kumar, and Sutara Suwanda from the following university. Now, some background information. We have seen that there are interesting oceanographic features that develop around the Cape, in particular Point Sal, and that these features are also generated in the current generation of ocean models. And you've seen some talk on the multiple level of nesting of the regional ocean modeling system. So the main question that I'm going to address is, can we predict the ocean conditions around a coastal cape like Point Sal? And two, what is the dynamical basis for the predictability that we find around the cape? Now, of course, there are different dynamical bases for predictability. One is the initial condition, or if you like, the decay dynamics of the initial state, for example, the circulation adjustment associated with complex topography. Two, the surface boundary condition, that is, the direct forcing by winds and heat flux along the coast and inner shelf. And last but not least, remote influences associated with open boundary condition, such as the influence of external and internal tides that sweep through the domain, or the submesoscale features interacting with the inner shelf from the offshore region. With that said, we'd like to investigate these dynamics in the context of the DRI experiment that took place between August and November of 2017. And in particular, for this experiment, one of the goals was, one, to develop an experimental forecast to aid the field campaign in real time, and two, to diagnose the dynamics underlying the forecast scale in the model. As you have seen, during the DRI experiment, there was a wide array of measurements and observational arrays that were put in the water. And so the idea was that we would use the modeling setup to essentially provide these real-time forecasts, and in particular, a 2-day experimental forecast. The way the forecast was set up is we had an outer domain model grid here, a 3-kilometer resolution that was used for a forecast by the UC Santa Cruz group. And this forecast was essentially integrated with the COAMPS hourly atmospheric forcing. And so here it's important to note that the COAMPS data actually does have data simulation to initialize the forecast, but the ocean model itself is only forced by this atmospheric product. So the model essentially is just the forecast scale really comes from the atmospheric drivers of the circulation. The lateral boundary condition also are set to the HICOM model, which I believe is also data simulation. So then this particular 3-kilometer output is downscaled to 1 kilometer, to 600 meter, to 200 meters, all the way to the 200-meter grid. And then this 200-meter grid was used for the forecast that was posted on the web in real time every day. So to summarize, every day we would just perform a 2-day forecast. Then the next day we would start again and perform another 2-day forecast, and so on. And all this was run with this experimental Phyton engine that was developed at Georgia Tech. Now I will spare you the details of the Phyton engine, and this is a website where the forecasts were posted, but the main scientific question is, how good are the forecasts? Well, it turns out that at the end of the field work we had access to the buoy data, in particular temperature at this location. This is a 3-meter temperature from August to November 2017. And when we compared to the model, we found that the average correlation scale, the time series at this buoy location, was R equals 0.78, which is quite high and significant. And this is an example, a visual example of the time series from the model, which is here plotted in blue, and the observation, which is plotted in red. And again, these are 3-meter temperature observations and models. We can also zoom in closer to Point Sal in this region and look at the buoys that are to the north and to the south of the Cape. And again, we found that the model had quite good skill in the forecast of about correlation of 0.68. And again, this is a visual inspection of the data. In blue, the model, and in red, the observations. And we can see that it's quite tracking quite well. And this is temperature, again, at 3 meters. So the question then becomes, what dynamics control the predictability? And again, the things that we'd like to explore are the role of the initial condition, the role of the surface boundary condition, and the role of remote influences, open boundary conditions. To do so, we will start with a set of predictability experiment in the model, where essentially we take the model and we run an ensemble of runs to test the different role that initial condition, surface condition, and boundary condition play in the predictability of the model. So in this particular experiment, for example, what we do is we set the initial condition to a climatological mean. That is, we take the long-term mean over this period, and that's going to be our initial guess of the initial condition. However, we retain the exact surface and boundary condition. So in this particular experiment here, we start, this is one buoy location, for example, the mean average condition, and then we run the model for 10 days, and we compare the trajectory of this model with the one obtained from the hindcast, which we consider here to be the truth. And you can do it a second time, and you can do it many, many times. And here I'm showing you 10 members of the first ensemble. And so if you look at this time series, what you find is that there are times in which the model initial condition is far from the truth, but the model can actually recover the trajectory even when the initial condition is far from the truth, like in these two locations. However, this is not surprising because it turns out that the time scale it takes for the model to recover is in fact the time scale of recovery is consistent with advection from the open boundary condition. And that makes sense. So the next experiment is really to also relax the open boundary condition and set that to a mean climatological value so that we can essentially see what is the role of surface forcing when we have a climatological initial condition and a climatological boundary condition. So let's perform the same ensemble again, now with the boundary condition set to climatology. And if we, for example, focus on ensemble number 4 and 9, we find that now the model is not able to recover essentially the mean state. But if you look at the variability, actually the variability is not that bad. In fact, even though the mean state, the model cannot recover the mean state, in most experiments, the variability, that is these kind of wiggles here in the 10 days forecast, is captured. In these two particular cases, the correlation is about 0.56. However, it's also interesting to note that there are some times, like this location here in time, this ensemble 6 and 10, where we find these huge kind of intrusions of warm waters from the south that of course cannot be recovered without the influence of the boundary condition. And these are poleward advection event of warm waters, and these actually are only controlled by the boundary condition from the south. And so in this case, for example, even with the surface condition, you can't really capture these events or this type of variability. And you can see here also there's some kind of hint of a poleward event. So in general, we can say that the surface forcing controls the relative variability on daily timescales, but it's not the only driver of the predictability. Now, the last experiment that I'm showing you here is one where both the initial condition and boundary condition are now exact, and in contrast, the surface forcing is set to a climatological mean, which is in this case a daily cycle. If we control, for example, ensemble number 4 here, where we had this, actually it's this one over here, you can see that essentially in this case the variability is not well reproduced, although the mean state is kind of captured. If we look at down here, we can see that overall there's this intrusion event that is captured and this other intrusion event that is captured. But if you look at the variability of the wiggles, we find that the correlation is not as high. So with that said, we can say that both remote forcing and local forcing control the predictability at different times. So let's try to quantify this a little bit better, and we'll do that by estimating the time propagation of the forecast error along the coast. So we're going to take a transect that follows the coast here, and then we're going to see the error along this transect as a function of time. And so, for example, this is an example of this transect for the experiments that have the initial condition set to the mean, so essentially climatological initial condition, but the exact surface and boundary condition. So the way to read this experiment, this is the temperature again, and so we're looking at the root mean square error in degrees C, and so here this is essentially root mean square error at time 0, and you can see it's very high because we have an initial condition that is set to climatology. But then as the model runs forward in time, you looked at the root mean square error from north to south along this transect is decreasing, and this is consistent with the idea that the boundary condition have some kind of restoring effect, as well as you have the exact surface boundary condition. So in this case, you can see you recover quite fast, especially in the southern region of the domain. Now we can do the same experiment now where we also set the boundary condition to climatological values or mean. So this experiment has only the exact surface condition, and here you can see that the errors, the scale is much higher, And in particular, there's a region here in the south that develops with very large errors, and these errors are really associated with the missing poleward advection events, these intrusions from the south. Last, we can do the experiment where we set the initial condition and boundary condition to the exact values, but we prescribe a surface condition that is climatological, in this case a daily cycle. And in this experiment, what we find is that the errors associated with missing surface forcing develop in the interior and northern part of the domain, and they're quite strong here, root mean square errors above 1. So a few concluding remarks from this preliminary analysis is one, the experiment forecast model for the DRI fieldwork exhibits significant forecast scale, on average a correlation scale of 0.7 in the upper ocean temperatures. Two, an analysis of the predictability dynamics reveals three things. First, both remote and local forcing are important in the predictability during different times. Second, the poleward intrusion of warm waters dominates the predictability close to the southern boundary. And three, the surface forcing exert a dominant control in the interior and northern part of the domain. Now, this is preliminary work, and a more in-depth analysis of the predictability dynamics of stratification from buoy data and currents from the ADCP data and bottom pressure is currently being performed. Thank you very much for your attention.